Okay, thank you very much, Jacobo. First, I'd like to thank very much the organizers, Jacobo, Ramon, and Mario, for the opportunity to show you our work here. I'm very humbled by the very impressive physics that has been presented in this workshop. So I'm not really from that field. I'm more a material scientist with a background on spintronics, magnetism, and ferroelectricity. But for quite some time, maybe more 10, 15 years, we've been working on these oxide two-dimensional electron gases, which have superconducting properties and also spin-orbit coupling. So mostly we've been harnessing the spin-orbit coupling for spintronics purposes, let's say. But we are trying also to play with superconductivity now, and I hope that you will find some interest in this new possible platform for topological superconductivity. So I want to, here basically you see the co-authors for this work. This is Hugo and Srijani, who did most of the experiments in this work. This Hugo is a PhD student from our group, and Srijani was a postdoc, and now she has a position in her home country in India. I want to acknowledge also all our collaborators, in particular Nicolas Berjal from the ESPCI, who is really our main collaborator for all the low temperature superconductivity measurements for this work. Okay, so I think there was a little bit of a few talks about oxide, complex oxide already, in particular from Javier Villegas. But just in a nutshell, we work with these oxide perovskites, which have this general formula. And as you perhaps know, they have a very flexible structure. You can really have many different compounds with almost the same crystal structure, which means that you can combine them into heterostructures with very clean interfaces. And typically at the interfaces, quite often you are going to find some new physics. And this is just one example. There are, of course, many in the literature of a quite sharp interface, actually atomically sharp interface between two compounds. This is a nickelate with metal insulator transition. This is just a conventional insulator. But the possibility to combine this material into almost perfect heterostructures brings a lot of exciting possibilities. You typically are going to have a reconstruction of the orbital, lattice, and chart and spin degrees of freedom at these interfaces. And you may have some topological properties arising from the combination of inversion symmetry breaking and spin-orbit coupling. And of course, then you can play with these external stimuli to act upon this new ordered state. Okay, so one typical example is this so-called LAOSTO, lanthanum aluminate transfer titanate system, which was discovered in 2004 in Japan. These two compounds taken individually are wide bandgap insulators, but yet when you grow one on top of the other in certain conditions, basically you find a two-dimensional electron gas, a very thin layer of conducting material. And this is from a few years ago, many years ago actually, where we mapped with the conductive FM the location of the two-DEG, and we found it just a few nanometers in thickness. This is an upper estimate because of the finite size of the conductive tip. So these are the hallmark features of this system, this two-DEG. It has pretty high electron mobility for oxides. This is not comparable with what you have in the best graphene or 3,5 heterostructures, but the largest values are reach almost 100,000. It's in some rare cases. Typical values are a few thousands. You have superconductivity at low temperature, typically below 300 millikelvin. But the conducting state, the superconducting state is very sensitive to gate voltage. And you can tune in or out of the superconducting condensate by applying a gate voltage. And you can here see build this kind of dome-shaped phase diagram, which is reminiscent of that of the cuprates, of course. And together with that, you also have Rashba type spin-orbit coupling. You have some kind of a triangular two-DEG, so it's a system with broken inversion symmetry. So you expect to have Rashba spin-orbit coupling. This was first discovered from signatures in the low-temperature magnetic transport. This is a weak anti-localization. And if you do an analysis of this data as a function of the gate, as you can see, you extract value of the Rashba coefficient, which takes values up to maybe 50 millieV angstrom. And as you can see, this is strongly tunable with the gate. So you have a system that is Superconducting has a spin-orbit coupling and low temperature. Both properties are highly tunable with the gate. And this is in the same material, same electronic system. So you could perhaps consider using it for topological superconductivity. I just want to go back to the properties of strontium titanate because I cheated a little bit when I was saying that you take two insulators and you have a metal at the interface. This is true, but in fact, if you go back to the properties of strontium titanate, yes, it is an insulator, but it's quite easy to make it metallic. If you dope it with just 1 part per million electrons, it already becomes metallic. And there's actually several papers who looked into that, one by Cameron Banya, who said that this is the most dilute superconductor with 10 to the 17 carriers per centimeter cube. This compound is actually also superconducting in the bulk. But you can see that the high mobility is already observed in strontium titanate. So the talk of today is about another compound, which is potassium tantalate. So it has a lot of similarity with strontium titanate, the main one being that they are both quantum paraelectric, which means that at low temperature, their dielectric constant really increases very strongly, almost diverges, and then plateaus at about 20,000 in case of strontium titanate and 8,000 for potassium tantalate. They're both perovskites. Potassium tantalate is cubic all the way to the lowest temperature. Strontium titanate has a phase transition at 110. But again, if you dope it with electrons, this is very old literature from the 60s, it becomes a metal. You can see here, so I flipped over these graphs because, back in the days, people were showing as a function of the reciprocal temperatures. But you can see here the metallic behavior and the mobilities, which reach maybe 20,000 at low temperature. So I will come to the superconducting properties later in the talk of these compounds. But in terms of the other ingredients, spin-orbit coupling, it's in principle going to be more interesting than strontium titanate because tantalum is much heavier. It's a 5D element, much heavier element than titanium. So you should expect to have stronger spin-orbit coupling effects. Of course, if you want to have Rashba spin-orbit coupling, again, you need to build an interface. So you are not going to see it in the bulk potassium tantalate. But people started to generate, to create two-dimensional electron gases based on potassium tantalate, a little bit the same way as had been done a few years before for strontium titanate, growing in this case lanthanum titanate on top of a potassium tantalate single crystal, and you can see that you have metallicity and some relatively high, well, not very high, mobilities. And in this early paper, which was a 2-deg induced by accumulating a very high charge density with a pyridine gate, I think. Some weak anti-localization was also observed and fitted, and Rashba coefficient of about 70 millieV angstrom was observed. So it was higher. It's higher than what was found in STO, but not quite as high as one would expect from the, the fact that you have tantalum, which is a 5D element. So just a reminder of the Rashba effect. You're probably all very familiar with that, but that's a manifestation, of course, of spin-orbit interaction that comes into play when you have broken inversion symmetry. That's the Rashba Hamiltonian, which leads to a splitting of the bands along the K direction. Then when you have, in the simple two-band model, you then have two Fermi contours, and at each point in K, the spin is locked perpendicular to K. So you have this spin momentum locking with chiral spin textures in both contours with opposite chiralities. That's the Rashba effect. A consequence of the Rashba effect, which was discovered by another Russian theoretician, Edelstein, is what happens when you apply a charge current to a Rashba system. Okay? So if you apply a charge current to this system, what you're going to do, you're going to shift slightly these contours. And because of the spin momentum locking, you are going to generate an excess of spin density here and there with opposite spin directions, but there's much more blue spin than the red spin. So at the end of the day here, you're going to generate a finite spin density. So even in a non-magnetic system, if it has this Rashba splitting, you apply a current and you generate a transverse magnetization. And this magnetization can diffuse as a spin current. And so this is how you can do the conversion between a charge current to a spin current. So this is another way to do that different from the spin Hall effect that Javier mentioned this morning. And you have the so this is the called the direct Edelstein effect from Edelstein in that paper. And you have the reciprocal effect, just like you have the inverse spin Hall effect, you have the inverse Edelstein effect, which happens when you inject spins. And then if you do that, you shift the contours in opposite directions, which create a finite charge current. So this is a charge to spin to charge conversion, okay? And there's a figure of merit for this, but I don't want to go into the details. And to have an efficient conversion, you need a large Rashba spin oblique coupling and also a large relaxation time. So this is very interesting for us working in spintronics because you can do charge to spin and spin to charge conversion, meaning you can generate spins from a non-magnetic material and detect spins in the non-magnetic materials. So you could in principle do spintronics getting rid completely of the ferromagnets, which has a number of advantages. But here for this audience, probably the most interesting part would be to combine the Rashba with a topological superconductivity. And so one question that we've been asking ourselves is whether this can be realized in these KTaO2 decks. Okay, so how do we make these samples? So one way I told you is to grow a high-quality epitaxial perovskite layer on top of the strontium titanate or potassium tantalate. In fact, we were inspired by a group in Orsay who discovered that depositing a very thin layer of aluminum is enough to create a two-deck. The mechanism is then different, but at the end of the day, you have a two-deck. I will explain to you how this works. So we start with a single crystal of potassium tantalate. Now this is 001 oriented potassium tantalate. This is important to remember the orientation. It's 001 for the moment. And then we are going to deposit a little bit of aluminum by sputtering in our case. And to monitor what is going on when we do that, we do XPS and we look at the tantalum levels. This is before depositing any aluminum, and the tantalum spectra correspond to pure 5D stoichiometric 5D tantalum. And then when we grow aluminum, here 10 angstrom, 21 angstrom, we see these shoulders that corresponds to the reduction of tantalum, meaning that we are putting electrons in the system. So we're actually reducing the tantalum by putting aluminum. At the same time, the aluminum is oxidized, and so we have an insulating layer of aluminum oxide. And because of the reduction of the tantalum, we create oxygen vacancies. They create electrons. We have a two-deck. And we can check the interfaces between the two materials, which looks pretty nice. And from the transport, we see a metallic behavior, which is tunable by the thickness of aluminum that we grow. See that the resistance decreases. The more we put aluminum, the more carriers we have, and the resistance decreases. Okay. So that's quite an easy way to generate a two-deck because we all do all this at room temperature in the sputtering. So already, yes?
How do you know if the aluminum is not conducting?
Because I didn't show it here, but we can do XPS of the aluminum, and we see that aluminum is fully oxidized. Yeah. But that's a good question. I should include this XPS data. So several years before that, we worked with Andrés Santander in Orsay, and we were trying to image the band structure using RPES of this 001 KTO. And for that, we were not depositing aluminum. We were kind of breaking or cleaving, not really cleaving, but kind of breaking in situ single crystals. And these are the RPES data, which are not as crisp as you would expect in a quantum material. But in oxide, it's actually rarely the case. So the main feature that were identified were the presence of different types of bands, a relatively light band here with a slightly higher mass pair of bands here, and some states here with a very, very high mass. So we kind of tried to go back to measuring RPES with a hopefully higher energy resolution a few years ago. And this is what we got at room temperature. So you don't expect to have a very high energy resolution at room temperature. But in this case, the main features were kind of consistent with that early paper. But at low temperature, we generated the two-deck by depositing one angstrom of aluminum by MBE in situ. And we had much higher quality data. So this is the low effective mass band that we had identified. If you do some further analysis, you can also see a little bit that there is another one here. And then there is some spectral weight here, which I'm going to show with higher magnification. And if you have good eyes here, you can see there's actually 2 bands here and 2 bands, which is consistent with a pair of Rashba split bands. Okay, so there's a quite complex band structure with 2 pairs of bands, which have maybe a Rashba splitting, but very, very small and resolved by the RPS, and another pair of bands which are much larger splitting. And we estimate the Rashba coefficient to about 300 millieV angstrom, which is in this case much larger in the case of STO, as we expect from the presence of the tantalum. And this is, in fact, this experiments are very challenging. This is the first time Rashba splitting has been visualized in this type of oxides. Okay, so then we have another way to measure, using transport, the Rashba coefficient. And for that, we take advantage of the directed Einstein effect. If you remember, we apply a charge current, and this is going to generate a transverse magnetization. So in this case, the presence of the transverse spin density is going to modify the scattering rates in the system. And at the end of the day, we end up with a longitudinal resistivity, which is going to comprise 2 terms. And this one is the most important. It is going to have a unidirectional dependence. Okay, it's going to be unidirectional with the magnetic field in the plane. So that's why you have this sin theta dependence. And it's going to be proportional to the Rashba coefficient alpha and to the current and the magnetic field. So that's why it's called a bilinear magnetic resistance, because it's linear with the current and the magnetic field. And there is also this additional term which arises because of scattering in between the 2 contours of the Rashba split bands. So then we do angle-dependent transport measurements. We rotate the magnetic field in the plane with respect to the current, and we fit the data with this expression, and we extract the different parameters. So this is actually the data we get, and we measure for positive or negative currents. This term is not going to depend on the current sign. This one changes sign with the current sign. So then we can isolate the different terms by doing half sum and half differences. And this is the bilinear magnetic resistance, and this is the other one, which we call the quadratic MR, because it's QMR because it's scaled with the square of the magnetic field. And this one really scaled with linearly with the current and the magnetic field. So it's bilinear indeed. And from the amplitude of these 2 contributions, we are able to extract the value of the Rashba coefficient. Unfortunately, it also depends on the G factor, which is not very well known in this system. So we just get some kind of range, making an educated guess on the values of G. But we get values which are, I would say, quite compatible with the values obtained in RPES, and certainly larger than what we found in STO. We did this exact same experiment in STO a few years before. So we kind of confirm that the Rashba coefficient is actually quite significant in the system. Okay, so now let me go to the superconductivity part. So I told you already that some titanate is a superconductor at low temperature with very low charge densities, all the way down to 10 to the 17. In fact, it is superconducting for the most recent data. And the 2 decks, STO2 deck, are also superconducting with a TC, which is about the same, 300 millikelvin. So this was known since the 60s. And since the similarity between STO and KTO was manifest already in the 60s, people, of course, looked for superconductivity in KTO and potassium tantalate. And there was a very intense search, and in fact, no superconductivity was found. People tried to dope the material with different means, and it didn't work. They couldn't find superconductivity down to 10 millikelvin. And this is a paper, I don't have the reference, it's from maybe the early 80s, which kind of summarizes maybe 20 years of search or 15 years. And this changed actually in 2011 with that paper from a Japanese group who worked with 001, potassium tantalate, still 001, and it will become important in a minute. And they were able to induce a very large chiral density and to create a 2 deck. And finally, they found a very low TC superconductivity with a low TC of just 40 millikelvin, with very high chiral density, 410 to the 14, which is about 1 order higher than in the case of STO2 decks. Quite surprising. But the situation again changed 10 years later, in 2021, when a group from Argonne found that if you then work with 111 oriented crystals of KTO, you have a TC which is 2.2 Kelvin. So much higher than in that previous work, and much higher, about 10 times higher than is from titanium. So this was really unexpected, but it's been reproduced, and it's actually a very robust result. So you can see here, for instance, that they generated 2 decks on 001 with pretty high carrier densities. None of them are superconducting, while these are all superconducting. In here it's 111, it's 001. So we jump onto the bandwagon, and we also try to make 1112 decks. Again, we generate the 2 deck by growing aluminum, and this is the tantalum levels before growing the aluminum and after. And you can see from these shoulders that we have a reduced KTO, meaning that we have a 2 deck. And this is the aluminum. Actually, in this case, we have the aluminum. We can see that it's purely oxidized aluminum 3+, even for 1.9 nanometers. So the aluminum does not contribute at all. And from TEM, we have a relatively clean interface. Of course, the aluminum oxide is amorphous, so we don't see the nice alignment of the atoms. But the interface seems to be pretty clean with very little interdiffusion. And we have superconductivity. So we played a bit with the condition, the thickness of aluminum, and we found a TC. Now our best samples have a TC about 2.2, 2.3 Kelvin. And there seems to be a trend with the carrier density, consistent with the work from that first paper, from the science paper from the Argonne group. And we measured the coherence strength, which is about 24 nanometers. We also did RPES of the 111, which is the data are not quite as nice as for the 001, unfortunately. We were able to feed the data with a tie binding model, again, inspired from the one we had for KTO001. Here we do not see direct evidence of Rashba splitting, but taking into account all the different parameters, we can estimate, we can see a little bit of splitting here from the fits. And yeah, we think the minimum value is about 20 milliviangstrom, which is quite small. You can see here the spin textures from these different bands, and there's a small separation here and there, and some anisotropy of the Rashba coefficient depending on the direction gamma k or gamma m. So we again did these angular dependent measurements for the 1112 decks. The data are a bit more noisy because the mobilities are not quite as high as in the 001, but we see some kind of linear dependence of this term with the magnetic field, as we should, and of quadratic dependence of the other term, as we also should. And we do this for 2 different directions, and we extract some values which are, again, with a larger R bar because we don't know the G factor, but they seem to be larger than what we were estimating from RPES. And we confirm that there's a quite strong anisotropy, which is consistent. I mean, the sign of the anisotropic is consistent with the earlier data. But it's really a pity that we don't have higher quality RPES data. It's very difficult. So superconductivity. So just like in the case of the STO2 decks, we can apply a gate voltage, and we can suppress superconductivity. These are 2 different samples. But here I've replaced the gate voltage axis by the conductivity in the normal state, and you can see that we kind of recover this kind of dome shape behavior. And so we can certainly suppress or, tune in or out, or in or off or on the superconductivity with the gate voltage. We are currently trying to make more experiments to try to get more insight into the superconducting states. These are some superfluid stiffness measurements from our collaborators, Nicolas Berjal at the SPCI. So here we measure the kinetic impedance of the superconductor, across the transition, and we determine the superfluid stiffness, which we can then plot as a function of temperature. And at low temperature, the scaling suggests of a possible strong coupling, okay? And but there's a deviation. If we go to higher temperatures, there's a deviation. The pure BCS strong coupling fit doesn't work, and we need to go to a BKT scenario to be able to fit properly the JS dependent with temperature together with the dependence of the resistance with temperature. Okay, so you have more details on this paper, and the theory was done by Larab and Fato from Rome. And these are the most recent experiments that we did, which are still unpublished. We are struggling to understand them. These are tunneling experiments. So here we use the aluminum oxide as the tunnel barrier, and then we have relatively large gold top electrodes, and then we do tunneling into the 2-deg. So this is a very nice, I mean, for us, for this oxide 2-deg community, nice gap. This is the best data that was reported in the case of LAOSTO. So we see here we are able to see really zero conductance at the bottom here. This is, of course, because the TC is much higher. It's about 1 order of magnitude higher. So I mean, at first sight, maybe you think that there's just one gap, but if you look in more detail, it's not so clear. We have these kind of small features here, which we have seen in different junctions, and we don't know really what they are. So we are just struggling to analyze this data. And we have fitted the data as a function of temperature, and this is the results. That's the gap as a function of temperature, and this is in contradiction somehow with the previous result from the superfluid stiffness, because here it seems to be consistent with the weak coupling limit. So it's just work in progress. We want to find ways to reconcile the microwave measurements and the tunnel data. If you look a little bit more details, as I say, maybe you have 2 gaps, or maybe the symmetry of the gap is a little bit different. Maybe there's some recent paper in Nature Physics with a completely different system that has gaps, features that look like ours, and the analysis is with a P minus IP order parameter. In fact, as I showed you, we have multiple bands, so perhaps it should be expected that we have different order parameters. So what do we need to be able to do this very nice fancy experiment that you guys were showing yesterday in particular? Well, probably this is a very long way to go, but I just want to flash very quickly some efforts from the community by ourselves to make quantum nano devices. So this is some data on quantum point contacts with a nice quantization of the conductance. Early preliminary results that we got recently with Nicola on quantum dots, and efforts from the group in Copenhagen to move towards double quantum dots. And actually now we have a project called eCaro. We just started, in which we want to do quantum dots and qubits with STO2-degs. So just in a nutshell, this is a table summarizing the advantages and disadvantages of these platforms. Just 2-degs. We have superconductivity in all of them. Actually, in the case of KTaO3 it's a much higher TC. It can be tunable. We have spin-orbit coupling, which is moderate and has to be confirmed in terms of its value. We also have data, which I didn't show here, which show that it can be tuned by a gate voltage. We are currently making top gates devices. We have some preliminary results. And we are also making quantum devices as well, and quantum coherence, qubit manipulation of the information in the qubits have not been demonstrated yet in any of the systems, but we are also working on that with Nicola. So in summary, I think I'm a little bit late, so I'm gonna flash my conclusion. So hopefully I've shown you that these are a new platform, new material platform, which can be interesting for topological superconductivity, because unlike other platforms, you have in the same electronic phase superconductivity and spin-orbit coupling. So that's probably an advantage, although there are other inconveniences in terms of the materials, processing, etc. I want also to mention that it's possible to make these 2-degs ferroelectric or magnetic or both. Okay, for some titanium, we demonstrated it. So this gives also a possible new degree of freedom to manipulate information if you move to quantum devices. And that's it. That's a picture of our group. And I want to acknowledge funding from these agencies. And thank you very much for your attention.